Alright, so here we have a troublesome quiz question. So let's see if we can work our way through this. So first off, it tells us that the acceleration due to gravity on the surface of planet A is about 1/10 that of the acceleration on the surface of planet B. So what that's telling us is that the value of G on planet A is 1/10 the G on planet B. Additionally, this will probably be helpful to us later. Let's go ahead and figure out what G is. So there's two ways to calculate the gravitational force. If you're on the surface, it's m times G. And if you're not on the surface, it would be more convenient to calculate it with the universal gravitation law, which is G mass of the planet times the mass of the object in question. And generally speaking, I like the big M for the larger object and the little m for the smaller object. I know if you look this equation up online, many times you will see M1, M2, but I have great difficulty keeping M1 and M2 separate from one another, but I do not have trouble keeping big M, little m separate, so that's why I do it that way. Divided by the radius squared. Now, something that you might notice is fairly helpful here is that the little m's cancel out. So your gravitational acceleration is basically big G, mass of the planet, divided by the distance you are from the center of the planet squared, which also probably is going to be helpful to us. In fact, let's take that and see if we can make anything useful with it. So for planet A, the G for planet A is going to be big G, mass of A, divided by radius of A, because we're on the surface, squared. And for B, it's going to be also big G, mass of B, divided by radius of B squared. And all of that divided by 10, which would be the same as multiplying it by 1/10, which would put the 10 here, so the 10 is still there. Okay, to keep the mathematical statement true here. Now, before I continue on, there's a couple of rabbit holes that I'm going to have to go down, but I'll go down this one first. So let's deal with this density thing. So what is density? Density is mass divided by volume. And specifically for a spherical object, density is mass divided by 4/3 pi r cubed. And if we're going to do density of A divided by B, that's going to be mass of A divided by, mass of A divided by 4/3 pi r of A cubed over mass of B divided by, again, 4/3 pi rb cubed. And conveniently, some of this stuff will cancel out. So the 4/3 and the pi go away. And then basically we need the mass and the radius of both things to figure this out in some kind of terms. And right now we have ratios, so we should be able to work out somehow or another to find this information, or rearrange in some manner to work that out. So I'm going to come back over here to these equations. Big G cancels out over here, and let's see, I think we need an expression to well, let's see what we can work out here and plug it in. Get back to the black pen over here. They also tell us that the radius of planet B is, the radius of planet A is 1/4 of the radius of planet B. So RA equals RB divided by 4. So I think I'm trying to figure out how to make this not be super complex, because we will be able to substitute everything in and make all the variables cancel out, and we'll just have a numerical answer left over. But trying to make that not look super complicated might be a bit of a challenge here. So I guess I'll just go ahead and substitute here. So I'm going to take this and I'm going to plug it in place of RA. Alright, so that's going to give me MA over RB divided by 4 squared equals MB over 10 RB squared. And MA I'm going to go ahead and save myself some trouble here. So the RB's are both in the denominator, they're both squared, so they're both going to cancel out. Okay, so MA divided by 1/16, excuse me, equals MB divided by 10. Scroll down a bit there. Now, we just got to do a little bit of rearranging here. So, 10 MA equals 1/16 MB. And I think we're here 160 MA equals MB. Multiplied both sides by 16. Which means that MB is a much heavier planet than MA. Planet B is much heavier than planet A, which shouldn't surprise us because planet B has quite a bit stronger gravitational field, and it also is bigger. So I guess that makes sense. All right. So now I have a way to express RB in terms of RA or vice versa, and I also have a way to express MA in terms of MB. So what that means is I can do a couple of substitutions. Again, I'm going to take this RA equals RB over 4, and I'm going to put that here. And I have a way to replace MB with MA. So I'm going to do that here. And then a bunch of stuff will have to cancel out, but it should all work. So let's see if I can do that and get all the algebra stuff to play out nicely. So, and not use up all of my video here. This is turning into a very long one. Alright, so MA divided by RB over 4 cubed. That's going to be divided by, we got to replace MB with 160 MA. That's going to be divided by RB cubed. Scroll down a bit here. And all I have to do is just deal with all of this stuff. Okay, so first off, MA in the numerator, MA in the denominator, the MA's cancel. RB is cubed in both of these, so the RB's are going to cancel out. And then what I have left is essentially 1 over 1/4 cubed over 160. Okay, 1/4 cubed. 4 times 4 is 16, times 4 is 64. So that is 1/64 over 160. And that is the same as 1/64 times 1 over 160. Okay, I realized I made an algebra mistake here because this is 1 over 1/64, which would just be 64, not 1 over 64. So that should be 64. And then that would make this just 64 over 160. So whatever decimal equivalent is the ratio that is desired there. Or 2/5. Okay. And that is truly unitless because it is a ratio of densities. And I suppose if you wanted to, you could have made up some numbers for these things and plugged in and found the density of each planet and divided them to also get a ratio, and it should have came out to be the same, providing you did all the math correctly. And there's a lot of stuff going on there. Hope that helps.